Okay, so this problem says, what is the capacitance of a large Van de Graaff generator's terminal, given that it stores 8 millicoulombs of charge at a voltage of 12 megavolts? Yeah. A Van de Graaff generator is just essentially a large metal sphere, and you're charging this. Okay? And the capacitance in terms of its dimensions, where A is the radius, is given by 4 pi epsilon naught times A. Okay? The radius. The capacitance is also given in terms of charge and voltage like that. Hey, Joe, if you want to be on the phone, you can leave the classroom. Okay? All right. Okay, so this thing works out to 0.67 into 10 to the minus 9, and coulombs over volts is farads. So the capacitance is nanofarads for this for this Van de Graaff generator. This problem says, if the capacitance per unit length of a cylindrical capacitor is 20 picofarad per meter, what is the ratio of the radii of the two cylinders? Okay, so a cylindrical capacitor. So here's a cylindrical capacitor. A coaxial cable has capacitance like this. Okay, and the two relevant radii are the following: the inner radius of the outer cylinder, and the outer radius of the inner cylinder, a metallic device. Okay, the capacitance in terms of the geometry is given by this formula. Okay. So what they're asking for is the ratio of the radii of the two cylinders. They're asking for the ratio of this B over A, this fellow. Okay, and they give you the capacitance per unit length. So they give you the capacitance per unit length. Okay. So this is what we want to find. So log B over A equal to 1 over 2K, and K is the Coulomb's constant. Okay. So now we can put in all these values. And the Coulomb's constant is 9 times 10 to the 9. Farad per meter. Yeah. So let's take care of powers of 10. That's 10 minus 3. That comes to the top. So this works out to 2.78. Okay. And now to find the ratio, so okay, and these two are inverses of each other, so B over A equal to e to the power 2.78. All right, so the ratio of the radii is 16.1. They just ask you for the ratio, yeah. To solve for B, they would need to give you A. All right, so this problem says an empty parallel plate capacitor has a capacitance of 20 microfarads. How much charge must leak off its plates before the voltage across them is reduced by 100 volts? Okay. So here's a parallel plate capacitor, and the capacitance is how much charge it can hold per unit volt. Okay, so let's say this is the initial charge, and that's the initial voltage, and you can see that the capacitance is fixed. So if the voltage reduces, the charge reduces. Okay, charge must flow out. Okay, so here, let's say this is the final charge and the final voltage. Okay, and the final voltage is initial voltage plus the voltage it's reduced by, and this is 100 volts. Yep. So that's a negative 100 volts. All right, so QF is C okay, and the final charge is less, so this is CVI minus CVI plus delta V, minus C delta V. Okay, so that's how much the charge reduced by, and the capacitance is minus 20 microfarads, and it reduced by 100 volts. So 2, and what are the units for charge? Coulombs. Farad times volts is a coulomb. Yep. Okay, in this problem, you have this bank of capacitors. Okay, find the net capacitance of the combination of series and parallel capacitors shown below. Okay. So when you do problems like this, well, generally you have something like that because this little capacitor is doing one job, this guy is doing another job. See, this entire thing is connected to battery, and all these are doing their own jobs. All right, so when you analyze this, you had to first reduce this to a single capacitance. Okay, so if you look at your notes, when you have a series combination, this is how the capacitances add up. And when you have a parallel combination, here's how the capacitors add up. Okay. All right, so in this diagram, these two guys are in series, so we'll reduce them to a single capacitor using this. These two guys are in parallel. We'll reduce them to a single capacitor using this. Okay? So I'll do them on the side. 1 over C equal to 1 over 5 plus 1 over 3.5 microfarads. Those are, and so C is okay, so when you have capacitors in series, the equivalent capacitance is always smaller than any of those guys. And you can see this guy is smaller than 3.5. Okay. So a series combination, you always get a smaller capacitance. Okay, and this parallel combination, this will be just the sum of those two, so it'll be 15.75 microfarads. Okay, so now what we have done is we've reduced this circuit to, this is 2.06 microfarads, and that is 8 microfarads. And I'm not going to write the microfarads. And then here is 1.5, and this is 15.75. All right, so we've done the first step. We've combined these two guys and these two guys. And now this is a series combination, and we'll reduce this to a single capacitor, and then those three will be in parallel. Okay, so that's what we're going to do. All right, so let me copy this. Okay, so we are doing a series combination here. And what will the series combination be? Do you have?
C plus whatever C2.
Yeah, its value will be less than that guy. Okay. so this fella, the effective capacitance here is 1.37 microfarads. Yeah. So now what we have done is 2.068, 1.37. Okay, in 2 steps, we've reduced this bank of capacitors to this equivalent circuit. Okay, and now that parallel combination is just the sum of all those guys. So that's 8, 10, 11.43. So this bank of capacitors is equal to this single capacitor. Okay. Yep.
Can you go back to the other slide? When you're looking at the photo, is it just trying to get all of the other ones to the middle one? I don't know what each capacitor.
Okay, so do you understand what a series combination is?
Yes, I
Okay.
understand the series and the parallel. I'm just, when do you know when to go from down up to side? Like which?
Okay, well, so you can't reduce this to a series combination because this is messing that thing up.
Just start
These,
repeating one loop at a time.
Okay.
Work out.
you have to have a clean series or parallel. So these two are parallel, these two guys are in series,
Okay.
and this effective one is in parallel with that.
Okay, so because if this was like an energy thing, then we would be redirected by going straight from 1.5 to the 0.75. So we have to combine 0.75 and 15 first. That's the idea.
Parallels before series, parallel before series.
Okay.
It doesn't have to be parallel before series, it just has to be a clean series, a clean parallel.
Okay.
These guys are not in series because this capacitor is messing him up.
Okay. Thank you.
All right. A 2 microfarad capacitor and a 4 microfarad capacitor are connected in series across a 1 kilovolt potential. The charged capacitors are then disconnected from the source and connected to each other with terminals of like signs together. Find the charge on each capacitor and the voltage across each capacitor. All right, so you have a Okay, so what you learned was when you have a series combination, what happens is the following. When you close the switch, electrons flow from here and they collect there. Let's say 10 electrons flow from here and collect there. Well, this guy's negatively charged. What happens then? These 10 electrons will repel 10 electrons from this plate. And this plate will get 10 electrons. And then what happens? These 10 electrons will repel 10 electrons from here, which will go there. So when you have a series combination, the charge that sits on each capacitor is the same. Okay? And again, this plate is negatively charged. So this, let's say this is minus 5 microcoulombs. That would be plus 5 microcoulombs, minus 5 microcoulombs, plus 5 microcoulombs. Okay? Well, so the question is, how do we find this charge? What you do is you reduce this to a single capacitor, find out the charge on that, and that's what's the charge on each one of them. Yeah? So that's the procedure. And that's why we learned in the previous problem how to reduce this to a single capacitor. Yeah. So here's the voltage, which is 1,000 volts. But let's first So C is 1.33 microfarads. Yeah. So our circuit is okay, so that's the equivalent capacitance. And now we'll find the charge on this guy, and the charge on this guy will equal these two charges. That's how charge, voltage, and capacitances are related. So Q is C times V, 1.33 microfarads times 1,000 volts. So, and that's farad times volts is a coulomb, and that's millicoulombs. All right, so now we found the charge on each one of them. Okay. Now what you're going to do is you're going to disconnect the battery, and they take these capacitors with this charge on each one of them and connect them in parallel. And so you're going to take these guys and connect them in parallel. All right, so when you connect capacitors in parallel, what happens is the charges redistribute such that what needs to be true? The voltage across each one of them is the same, okay? So now let's say this becomes charge Q1, Q2. Q1 over V should equal Q2 over V, and so C1 equal to Q1 over V, and C2 equal to Q2 over V. Okay, we don't know the voltage, but here's another equation you know. Q1 plus Q2 should equal 2Q. Okay, remember the charge before you connected them was Q and Q, and so when the charge is redistributed, the sum of the charges is equal to 2Q. All right, what are the two unknowns? Well, we know these guys, we know this guy. Q1 and Q2 are the unknowns. Okay, so this equation is really telling you, so this is telling you V is Q1 over C1, Q2 over C2. Okay, so Q1 over C1 equal to Q2 over C2. All right, so you have two unknowns and two equations, and you can solve this. Okay, so let's do that. So Q1 is C1 over C2 times Q2. We'll call this C1, C2. So 2 microfarads okay, so what we have found is Q1 is half of Q2, okay, and that makes sense. See, the voltage across them is the same. If the capacitance is half, the charge held is half for the same voltage. Okay. And we're going to put that in there. So half Q2 plus Q2 equal to 2Q. And Q was 1.33 millicoulombs. Okay, so that's and Q1 is half of that, which is 0.885. All right. So again, let me review this. And so there were several steps to the problem. Okay. So when you connect these two guys in series across the battery, you get the same charge. To find the charge, what you had to do was reduce this to a single capacitor, find the charge on that capacitor. That was equal to these charges. And then when you disconnect them from the battery and connect those guys across parallel to each other, what happens is the charges redistribute such that the voltage across them is the same. Okay. And so that's how you solve the problem. All right, so this problem says a capacitor has a charge of 2.5 microcoulombs when connected to a 6-volt battery. How much energy is stored in this capacitor? Yes, so the energy stored in a capacitor is that. Yeah. So 1/2, 2.5. No, I don't. Okay, coulombs times volt square is joules. So this is, and that is 36. 36 divided by 2 is 18. 18 times 2.5 is 36 plus 9, 45 microjoules. Okay? That's the amount of energy stored in there. You guys, if you remember your notes, in your cameras, the flash camera circuit, that stores about 20 joules. Okay, so 1,000,000 times more energy than this. All right, this problem says, suppose you have a 9-volt battery, a 2 microfarad capacitor, and a 7.4 microfarad capacitor. Find the charge and energy stored if the capacitors are connected to the battery in series, if they're connected in parallel. Okay, what you'll see is when you want to store more energy, what you want is a parallel connection. Okay? And when you want to connect, so parallel connection gives you more energy storage, okay? So, okay, so let's connect them in series first. Okay, so we find the equivalent capacitance. So the equivalent capacitance is 1.57 microfarads. Okay. And so the charge stored in it is C times V, which is 1.57. Okay. 14.2 microcoulombs. And the energy stored is 1 over C V squared. Yeah. C, there's the equivalent capacitance, and it's connected to a 9-volt battery, so 1/2 1.57 microcoulombs times. Okay, so 63.6. Yeah. Again, coulombs times volt square is joules, so it's 63.6 microjoules. So that's the energy stored in this series combination. Okay. Now we'll do the same thing for parallel connection, and I'm just going to do the energy. The energy is 1 over C V squared. And for a parallel combination, it's the sum of the two, microfarad, 9 volts squared. And so this works out to 380.7 microjoules. So you see this? In this series combination for these two capacitors, when you connect it to a 9-volt battery, you stored 60 microjoules of energy. And here you're storing 380 joules, 6 times greater amount. Okay. So if you read your notes, you'll see that those fusion reactors, when they fired the lasers at a little pellet, yeah, all those lasers were powered by a bunch of parallel capacitors in parallel that were charged. Yeah.
So when finding the charge of the parallel,
Mm.
you would do the Q1 over C1 equal to Q2 over C2 again?
No, so, yeah, well, charge is easy actually. Yeah, so Q1 over C1 equal to voltage, so Q1 is V times C1. And similarly, Q2 is 9 volts times. So 9 sevens are 63, and 9 times 4 is 36, so 66. All right. So this problem says, okay, so here's my plan. I'm going to finish these 2 problems in a minute, and then I'll finish the lecture on chapter 9 today, okay? So this problem says a parallel plate capacitor has a charge of magnitude 9 microcoulombs on each plate and the capacitance of 3 microfarad. When there is air in between the plates. The plates are separated by 2 millimeters with the charge on the plate kept constant. A dielectric with dielectric constant of 5 is inserted between the plates, completely filling the volume between the plates. What is the potential difference between the plates of the capacitor before and after the dielectric has been inserted? Yeah. So so the charge is 9 microcoulombs. So the capacitance with air in between them is 3 microfarads. And the capacitance with the dielectric present is this. And the dielectric constant is 5, so 5 times 3 microfarads, which is 15 microfarads. All right. What did they ask you? What is the potential difference between the plates of the capacitor before and after the dielectric has been inserted? All right, so the potential is Q over C. So, and we'll write V0 with air present, which is Q is 9 microcoulombs divided by 3 microfarads. Yeah. And coulombs divided by farads is volts, so this is 3 volts. So this is with air present. And the voltage with the dielectric present, you're keeping the charge the same. Yeah. And the and the capacitance now is 15 microfarads. Okay, so this is 3/5, which is 0.6 volts. So here's what happens. The voltage across the plates is the electric field times the distance between the plates. Okay, and when the dielectric is inserted, the electric field decreases and the voltage decreases. Yeah. So with the dielectric present, the electric field decreases, and so the dielectric strength is greater, you're able to charge the capacitor to a greater degree. Okay? In part B, they ask you, what is the electric field at the point midway between the plates before and after the dielectric is inserted? So now we'll calculate the electric field. Okay? So the electric field is V divided by D. Okay? So with air present, the electric field is, the voltage was 3 volts, and D, the distance between them was 2 millimeters. 2 milli is 10 minus 3, so this was 1.5 into 10 to the power 3 volt per meter. And with the dielectric present, electric field is, again, voltage over distance. The voltage was 0.6 volts and 2 millimeters. And so, again, the milli is 10 minus 3, which comes to the top, so 0.3. Okay. So again, you see, the electric field has reduced from 1500 volts per meter to 300 volts per meter by a factor of 5, which was the dielectric constant. So it reduces by that factor. So this problem says a parallel plate capacitor is filled with two dielectrics. Dielectrics are insulators, so this is filled with a dielectric like that, and you can see that half the volume is filled with this dielectric and half the volume is filled with that dielectric. Okay. As shown below, when the plate area is A and the separation between the plates is D. Okay. Show that the capacitance is given by this. So you see, this is the capacitance for an air-filled capacitor, and with this combination of dielectric field, that is the effective dielectric. That's what we're trying to show. Okay, now if you look at these two capacitors, see this guy is connected in parallel to this guy. Okay. So let's call this C1, C2. Okay. C1 is kappa 1 plus epsilon naught, and the area of this plate is half this area, A over 2, and the distance is D. C2 similarly is kappa 2 epsilon naught A over 2 divided by D. And these two guys are connected in parallel. Okay, so the equivalent capacitance is the sum of these two guys. So the capacitance is C1 plus C2. Yeah. And you see epsilon naught A over D is common, and kappa 1 over 2. Okay, so that's the effective dielectric constant. This guy is the effective dielectric constant. If you So there is the formula for a parallel plate capacitor with a dielectric present, and this guy is equal to that. You guys recall that dielectrics are put so that, well, they provide mechanical support. You can also charge them to a greater degree, and so on and so forth, because lightning happens in these things at a higher electric field. Yeah. Now, interestingly, see, this was the fractional volume. Okay. Now, if you have a bunch of dielectrics, you can show that this is so. Okay. So kappa 1, kappa 2, kappa 3. You can show that the effective dielectric constant is the fractional volume, and so on. All right, guys, so